So I want to start with I want to do diffusion language models. So we are so the these are primarily discrete diffusion models. They're going to be quite different. So I'll start. Essentially, it's a restart. Its ideas are similar to the kinds of things we saw, but I will do the notation again from scratch for this setting today. Okay. So the first paper to talk about these ideas was Dickstein et al. That's paper one. D3 and then this paper by Austin et al. Was sort of made this thing quite popular. These discrete diffusion language models. Two sort of important papers in this are sort of mass diffusion models. This is by Sahu et al. And Jeshen Shi et al. These two papers. So these are in terms of sort of the kinds of diffusion models. So maybe I should step back and talk about a little bit about the big picture. What diffusion models are doing is for language, you have a sequence of tokens, you fix a number of tokens, and you start with some initial condition, and then eventually you're going to get an entire string. Okay. So what is that initial condition you could start with? You could start with fully random, you could start with Gaussian noise, you can start with something else. So these variants are all different ways of sort of what you're starting with. Okay. So with that background, these papers were broad. I mean, you could say anything you want and said how these models should develop. You can specialize these models for a certain type of initial condition. We'll talk about this in a little bit more detail. These are called masked models. That's 3 and 4. You could basically say, I don't want to do mask. I want to just do Gaussian. I don't want to do language as discrete. I want to do it actually as continuous. Okay. Just think of a sequence of Gaussian tokens and do something with it. Okay. That is this one. Okay. Or you could say, I will start with a uniformly random over whatever the alphabet is, initial condition. Then that's this one. Or you could say, I want to go back to a flow perspective. Remember in DDPM and so on, we had two views. We had an elbow view and a discrete time view. We also had a completely flow view. Can you do these things using the flow view? There are these. Okay. Finally, even the flow view essentially just gives a theoretical construct. Finally, to actually implement it, to discretize it, so you'll get back to the same thing, but just a different way of thinking about it. And much of the notation is taken from 2.3 and also this paper by Ritu and others. For this, I'll get to maybe in the last class. Okay. So there are also many other diffusion language models, which I'm not going to talk about, but I've just given the references. You can these models are either new types of noising and architectures, or they're actually just scaling. So you can, if you're interested in going down this pipe, that's why I've written carefully a bunch of different models. You can Google and start reading these papers if you're interested in doing more in this space. Okay. I also want to talk Litu for a lot of discussions on these notes and figures here. Okay. So let's start with one type of diffusion language model. Okay, it's a mass diffusion language model. As you saw, there's a zoo of models before, but I'll just stick to one for concreteness today, and we'll see how far we can go with this. So I have this sentence: a cat is playing with a dog. Okay. I want to generate this. So analogy of images. We started an image. In some way, we noised it to get pure noise. Then we learned to denoise it iteratively, starting from pure noise, coming all the way back to the image. So let's try to push that analogy for language. So I have a language sentence. I need to come to whatever the representation of a latency. I need to move to some space in which I can diffuse. Okay. So that's the tokenizer. So for example, you could just use BPE, in which case you take this and create a sequence of tokens. In this picture, it's just arranged as a grid. It's actually maybe a better way to think about it for language is just a string, the way you think of it in autoregressive. Just drawn this way, sort of, because we have been thinking of images so far. So we just displayed it here as a box. Okay. And each one of these tokens is an integer from the vocabulary. So if you're using GPT-2 type, whatever BPE, there's 50,000 odd words in this vocabulary. So each token here is simply an integer. That's all. Each one is a different integer, which is how we represent it, we'll worry about it later. But that's all each token is. And so you have a sequence of tokens. So let's say for concreteness, 4,097, 4K tokens. Okay. So we just arrange those 4K tokens in this grid. You want to noise this. There are different possible noising models. One possible noising model we'll spend a lot of time today is the masking noising model, which is you take any one of these tokens and just randomly erase it. So create a new word in the vocabulary called mask. Okay, right? The intuition is just a blank, and go to that state. For example, this orange token has become blank here, and once it becomes blank or mask, it just remains mask forever. For some other thing, maybe this one, it's remaining the same. At some other point, it becomes mask. Eventually, every one of these things become mask, and the terminal state, you have all masks. So this is your noising model. It's not a Gaussian noise, it's a mask. Okay. So the notation, your initial is X. Then this is Z0, the latent Z0 all the way up to Z1. If there's T steps here, then this is indexed by 0 by T, 1 by T, 2 by T, all the way up to T by T. That's your indexing here, time index. It's moving in discrete steps, and that's where we are. All right. So this, for those of you who have sort of played a lot with autoregressive models, here it's very different in the sense that we are not talking about an arbitrary length sequence or any such things. We have already figured out how many tokens we are going to deal with. It's fixed, pre-decided. In this case, there are 16 tokens, and the final state will be 16 masks. And then you'll see how to get these things back. Okay. So we need to think about how to train this and the inference with this. So in terms of, first, let's look at the inference side of this thing. Okay. So now we have drawn this as if you look at this sequence, okay, this is the noising process. Presumably the inference process would start from here. You have some model to go from here to here and sequentially apply this thing all the way to get this back. Okay, that's the inference process. So at some point you're here. How do you go from here to here? In terms of how the pipeline, so you have that same colored rectangle is now written as a line. So some have been unmasked. So there's this A, which is the integer 64. There's is, which is the integer 318 in the tokens. Width, which is integer 326. And the rest are masked. The masks all correspond to this integer number. So that's your string. Okay. And you have some box, which is now going to predict the next one. It may predict one or more. You can, in principle, decode any number. What it's going to predict is, this box will predict for each masked position. It will predict logits on what it could be. And you come up with whatever way to sample from these logits. Maybe you unmask one, you unmask two, whatever, depending on whatever the strategy is. We'll leave those things vague for now. Okay. In this example, we just decided to unmask one thing. Unmasking essentially means takes one of this and then replace it, and then look at the logits associated with it. And from those logics, a sample to get what a word could be. And I'm just giving you a potential pipeline of this system. Again, stop me if something is not clear. To predict this thing, you use all the currently unmasked tokens. In this case, these three will use through this thing to influence what this is going to be. Is the basic model pipeline clear so far? Okay. It's a block. Start from all mask, unmask a few more, unmask a few more, and this whole thing. The whole game here is to learn this reverse process. So this is the inference pipeline. So what do you do for an inference the prompt if you want to do question answers with this kind of a model? Okay, you will have to do, you have your base model, which you have presumably trained. starting from all masks to give a string. So essentially what you have learned is a sampler from the joint distributions of L-length integers. Okay, that's really what you have learned. Okay, because each token can be an integer between 0 to 50,000, 50 or a little bit more than 50,000. Okay, and so you have some joint distribution, and this box or steps samples from that. But suppose, yeah.
Masking is like the standard parsing.
I'm just talking about masking. Okay, I'll come back.
No one's doing anything else.
There are all these other models. By far, the most popular is masking because it gives the best performance today. It works the best. That's not to say that it will always work the best. People have just scaled up the masking models. The other models have not been scaled up. But at moderate scales, masking was way better. And there are reasons why. Again, I'll talk about that when I talk about other models, if I have some time. Or what's the advantage of masking? Sujay.
There are things like edit. I know you're not talking about, but you're talking about pixel.
Yeah.
But there are these models which like insert, delete.
Yeah.
So aren't those better? They have come more recently.
Yes.
So, MBL has already like 2 years old.
Yes, I'm just talking about one model here. This is a class. I mean, this is a right. I mean, you know, yes, there are all these other models, but before you could even for the uniform model, is this bad? Well, there are actually ways to make it work in an intelligent, interesting manner. But I need to pick a model to actually go through the whole pipeline of training, inference, blah. So I'm just going to stick to this. Okay. Yeah.
Previous diffusion case, the actual true distribution is going to a kind of normal distribution.
The noise was a high dimensional, not Gaussian distribution.
The distribution, but in this case, I see all are masks.
Good. This is an absorbing state. You can think of it as going to the all zero. In the image case, it would be something like you don't become a Gaussian, you just collapse to the zero vector, quote unquote. That would be it's an imperfect analogy, but that's the kind of analogy that is here. Okay, so so you could instead say, I want to go to this, I want to go to a random initial final state. Okay, some equivalent of what Gaussians might be. Okay.
Denoising case, you're just starting from all.
It's a Markov chain. So it's not you are always training a Markov chain to go. It's an absorbing Markov chain. You start from the state space is a length L of each. It's an integer. Each one of these tokens can be an integer between 1 to 50,300 roughly, and you got a string of so many integers. So this is your state space. Look at all possible such strings. And what you are trying to do is learn a Markov chain to start from a particular initial state, which is all masked, and figure out where to go to the next state. And more generally, wherever you start, learn to go to the next state. That's all you're trying to learn. Okay. Okay. So I'm going to use the because I'm going to stick to only the mask model and not any of the other models, at least for today's class. I will use the notation from sort of this paper, the D3PM, which is the Austin et al. Paper, but also use some notation from these other 3 papers, okay? MDLM, MD4, and ADLM. Notation-wise, this I'm going to call Z0 equal to X, at least for the beginning. Though in practice, Z0 and X need not be the same things. You could do a post-processing step to keep Z0 and X separate. I'll talk about that when I actually go into the nuances of how to define the loss function training. Okay. Sorry, before I forgot to say this one thing. How do I do inference now with this? You don't want to just generate a string of text. You don't want to start from all masks and generate a sentence. That's not a use. That's the base generative model. But really, you'd like to do some question answering or do something else with these kinds of models. So how you do that is basically you create such a string of prompt from prompt. That's your question and mask. Okay, you pre-decided what's your length of your prompt and your mask, and then SFT your model. Okay, with question answer pairs. So instruction fine tuning is what you would do to actually use this model. But I'm not going to talk. I mean, that's not the hard part. These parts is what people understand how to do with autoregressive models. So all that is just carries over. What we are talking about today is just how to train the base model. Okay. So the forward process, as we said, we have tokenized. You start with a L length vector, masking noise it all the way to get to all masks. Notation-wise, K is the vocabulary size, 1 through K. And the token sequence we are going to denote as X soup 1 to X soup L. And the way you're going to represent this is through one-hot encoding on the simplex. Meaning, we know that we said that these tokens are just integers, but that's not the way we're representing it. We're representing a vector of 50,000 dimensions with the ith with it being 1 in one of the elements. If the integer value is j, then the jth location will be 1. Everything else will be 0. That is the representation here. It's a one-hot encoding. Okay. Okay. And typically the last one is mask. When you're doing the mask thing, you take your vocabulary and concatenate one more word to it. Actually, you need to have some few other words also, which I'll ignore. Like end of, if you want to do prompt tuning, you need some special types of things you need to add to this. You can put a few other things in the vocabulary as needed. Okay. But I'm going to ignore all that. Just right now, we have a vocabulary and one extra mask, and maybe a few other things depending on what you want to do. Okay, now the forward process, I sort of hand-wavily said that you want to randomly mask and then stay as a mask, and I use a Markov chain word. So what exactly is this Markov chain? Well, the process is modeled as a time inhomogeneous Markov chain or a discrete state space. You start from X, you move to Z0. Typically, they could differ, but for much of what I'm going to talk about, X is Z0. Okay. When do you make these? We'll talk about why you want to keep this potentially different in some cases. But for the most part, X equal to Z0. Then you go to Z1, Z2, and Z1. Then this bad notation. It's not Z1. Okay. It's Z1 by T, Z2 by T, because there are T steps all the way to ZT by T. And two things we need to keep track of. I'll always talk about times S and T. S and T are not. T is a general time, meaning T is really T of I, which is I by T. S is always one time step before T. I can't do S equal to T minus 1. It's T minus 1 over T. It's just clunky, so we'll just call it S and T, with the understanding that S is always one step before T. Okay, S is not some general time before T. Okay, always that's the notation. Okay. So S is I minus 1 by T, and T is T of I is I by T. All right, now the forward process. We are going to design the forward process as the following. So there are two ways to describe it. I will describe two different ways and show that they're equal. So you can define it as the T-step forward conditional distribution, meaning you start from X and you can ask, what is the density, what is the PMF over ZT? Okay. Remember, these are all discrete alphabets, discrete time. So there's no densities in any of these things. These are all mass functions. These are just PMFs here. Okay. What's the T-step forward mass function? We are going to model this as product form, saying it's first of all, for the, look at the notation here, there's L and T. L is the location in the string, meaning maybe I should have this picture. So this could be the Lth location. So to figure in the noising process, this one to figure out when it becomes masks will not depend on anything else. Okay, if we just need to track this one thing. You can just look at that particular thing. That's essentially what the product form means. Okay, and so that's this product form. And what is that? Well, now just look at that one coordinate. Now we are just looking at the Lth coordinate in this. You start from pink and you want to figure out a time t, whether it's a mask or still pink. Okay. And the thing is that there's a time varying probability alpha t, which for any point in time t, it says it remains the same as XL, whatever your state was, with probability alpha t. With 1 minus alpha t, it has become a mask. Remember, this statement is not a Markovian statement. I'm just looking at what happens at time t. At time t plus 1, I don't even care about what happens at what had happened at earlier times or whatever. I look at X and tell me whether I'm going to be mask or unmask. Okay. This is one view of this thing. Okay. And once it becomes mask, it remains mask forever. And mask basically means it is this, all zeros and a 1. These alphas are chosen so that they're monotonically decreasing. Alpha 0 is 1, alpha 1 is 0, and at every time step, it goes down, the alphas. So pictorially, this is what is happening. If I just look at this point in time and this point in time and ask, is this green masked here or not? The probability that this has been masked at this time is simply 1 minus alpha t. That's all. Good so far, this model. So I will just do some notation and then we'll look at the Markov view of the same thing. Notation. So we are always going to be dealing with categorical distributions. There are and we will write R. So if you have a distribution R, if you've got two one-hot encoders A and B, which means remember, these are vocabulary length vectors. A and B is basically one at maybe jth. A has one in jth position, B maybe in one in some other kth position. Okay. So that means this distribution, this mixture, alpha 1 minus alpha simply means R of y is with probability alpha, it's j, with 1 minus alpha, it's k. That's all this means. Okay. It's just a categorical. You can use this categorical also to go beyond one hots and talk about just if A was already a vector which is not a one hot but actually a PMF, meaning A could be a vector who's non-negative and the sum of the coordinates is equal to 1, then again this notation makes sense. Okay. In that case, this simply means, say, let's call that C. It simply means that this PMF, say, let's say the underlying random variable is y, it would be equal to j with alpha times, look at this vector's jth position, okay, and let that vector's jth position be C sub j, then it would be equal to j with that position. And for j star, let's look at j star. Suppose B is one hot with 1 in the j stars component. Then what will you get for that? You'll get alpha Cj star plus 1 minus alpha. That's all. So we will use this notation, categorical notation, to either inside it could either be one hot vectors, it could be probability vectors. As long as alpha and 1, these are mixture distributions, we can interchangeably go between all these kinds of things. Okay. So given this, okay, now we have this notation. We had described the forward process as just looking at x, the x0, which is x, and looking at what happens at zt. Instead, we can look at it as a time, as one step at a time process as well. An equivalent description of what we did previously is the following. Suppose we know the state of a particular token L at time s. Remember, s is always one time step before t. Then what is the PMF at the next time step? The answer is it's a categorical distribution. It depends which is the following. It continues to remain ZS with probability alpha t by alpha s, and it switches to mask with 1 minus that probability. Remember, this is a valid probability because alpha t, the alphas are monotone decreasing. Okay, so alpha t by alpha s is less than 1. As usual, just like what we have been doing through the semester, we are abusing notation, but just to be consistent with literature. This ZT and ZS are encoding two things. So when I write P of X, it normally in a PMF, this X simply means whatever the value is. This is actually encoding two things. It is not only encoding value, this T is also saying that this Q, and this S is saying this Q is the transition for these times and for this coordinate. So we are encoding in the arguments of Q some properties of Q as well, which is bad notation, but this is what this entire community is doing it this way. So I'm just going to be consistent with the notation of this community. Okay. So if for example, therefore, these kinds of statements are meaningless, which in probability, these kinds of statements would be very clear. Okay, because I don't know what Q I'm talking about when I write this.
It was like some base measure that.
It's Q of it's really Q of T comma S comma L. Okay, there is some huge joint base measure, but I don't know which particular margin. If I say Q dot given dot, I don't know which conditional, which part, which coordinate.
Are random variables, not values, then like some.
Even then I can't, because the functions may be, Q function will be different depending on the S and the T. It's a time inhomogeneous Markov chain. It's not time homogeneous. Okay.
Yeah, but-
Anyway, I'm just calling it this way. It's not. We can take that. Anyway, I'm just saying that notation is awkward in the sense that you need to look at the arguments to actually figure out which one. That's all I'm trying to say. Okay. And so just to complete this, what is this conditional? It is if you continue to remain here with this probability and go to a mask with this probability. Okay. Now we have defined the same system in two different ways. Remember previously we just said it as one possible jump and this one as the one step. Are they equivalent? And yes, we just do total probability and Markovianness. So let's actually do this calculation. Okay. So let us say Z0L is XL, which is little xl. This is the sample. Okay. Capital letters are random variables, small letters are instances. So let's show that these characterizations are equivalent. So this is the T step forward characterization, which means that it is with probability alpha T, you remain the token. With 1 minus alpha T, you become the mask. So this is the T step forward. We'll further condition on, if I'm looking at T, look at one time step behind it. S is T minus 1 over T. So look at one time step back, condition on it, total probability theorem. This Markov, so given this can be dropped. Okay. So and now this token, we are dealing with a mask model. So all these calculations will differ when it's uniform, when it's something else. So that's why the mask is easy to write everything out, which is, we can write things for uniform as well. But for the purpose of this class, I'll just stick to mask. So which means that Z can be either XL itself or it's M, okay, in this case. So now, second again, bad notation, which is consistent with literature. We are going to write these kinds of statements. Okay. The first bad notation was that we are not putting any subscripts for Q. The second thing is this statement is an assignment. It's not an equality, meaning the following. This is not a random variable. So this statement of Q of 3 given 2 with something is clear what it means. What does this is, if I write Q of M given XL, now let's say that I have this. I don't know what I'm talking about because I don't know which time I'm talking about, what state to what state, which coordinate or any such thing. So I need to somehow specify which distribution I'm dealing with, which conditional distribution I'm dealing with at any point in time. And this is the notation used for that. Okay. This says that the way to interpret this is, I know that in the initial time I'm an XL. Why do I know it's initial time? Because I'm using the letter X. So it means that this is the initial time. Then I want to understand what is happening for the nth coordinate at time t. And I want to replace this by a mask. So that's what this equality here means. Okay. This is not a probability statement at inside. Yes.
If you have small z, you have capital Z.
Then I need to go to probabilities. That's what. So here's my definition. So formally, this is what this is. This is encoding this. Mathematically, this is the correct statement. Okay. But everywhere in the papers, which most of the papers you'll read this. Which is why I'm going through notation carefully, because otherwise at least it was very hard to read many of the papers till you actually figure out what exactly people are doing. And this is really what they mean by these things, which is why I want to use this notation, because everybody uses this and you're going to read the papers in this community. Yeah. Here?
The Q of ZT of L equals XL, it should be equals M.
I see. This one. Correct.
No, the other
No.
side.
No.
The
what the-
ZT of L equals XL, not Z. Because you're tracking probably
Wait, ZT XL equals, wait, sorry, I don't know what you're talking about.
So
So
the first two terms are the.
this is correct. This is correct. This one is correct.
No.
No. What should I change?
The left side, the ZT of the other one.
Oh, of course. Okay, sorry. I had no idea. Okay, yes. These are, thank you. Okay, all right. Yeah, I've just, yeah. For this probability, we have just expanded the summation, stuck various things in. Now, let's compute this thing. Now, if once I'm masked, I continue to remain masked. So it's 1. This, from the original characterization, was just 1 minus alpha s. This is, I don't know what it is. So I'm going to just leave that as is. This one, I know that if I start at XL at time S, the probability that I remain the same is just alpha S, because I'm starting from that original T-step characterization. So if I solve this, then I'm going to get the Markov thing. So just rearrange these terms, and you're going to get the one-step probabilities. And we'll sort of move between the one-step and the T-step all the time. Now that we have seen that these two are equivalent to each other. The other important thing we'll need to deal with is this thing called the reverse posterior distribution. So this is doing the following. I am at some time s, look at one time step in the future, and look at all the way at the start. So what is my distribution if I know this one and where I start there? Let's think about this mask model. If I know that on this side, the token is the same as what I started with, then I must be the same token itself. Okay, that's one case. The other case is there's a token there, this is masks. Then I could be masked or I could be the token itself. There are two values, and there are some probabilities associated with each one of them. So let's actually compute that. Okay. So I want to figure out the reverse posterior of ZS given ZT comma X. So which is nothing but ZS ZT ZX divided by ZTX. Okay. So which means it's Q of ZT given ZS and XL times Q of ZS given XL. I'm just doing the chain rule. Q of XL. These things cancel. Use Markovianness here. So this thing goes away here, which gives me this expression. Now we'll compute the cases. Okay. So as I said, suppose that to my future, it's still unmasked. Then I must also be unmasked, and I must be the same value, right, in this Markov chain, which means that ZS, in the case where in the future is still unmasked, then my distribution is just it's just what the future itself is. It's a delta function. The other case is when it's masked, and now the only question is, did I get masked at my step to the future, or did it get masked before? And so you can stick these. It's a very simple calculation based on what I said, that it's just 1 minus alpha s by 1 minus alpha t. Okay. So if you put various things together, then what you get is the following. In this case, the probability that it's still categorical at some point. If I know one step into the future and all the way at the beginning, I know the values, then the distribution I have is categorical. And these are the probabilities associated with it. I'm either masked or I'm the beginning token. These are the only two cases. Why are we doing all this calculation? Because it gets to the crux of this thing, which is what is the learned reverse process. So let's go back to this picture. What we are going to do is not the obvious thing, which is why we went through sort of all this careful notation. This is a forward process. It's a time homogeneous Markov chain. You could try to say, hey, let me write the reverse process, one-step process, Q of ZS given ZT. And then I don't know what this is. And then let me learn a ZS given ZT. Let me try to learn this. This is something which you could try to do. This is not what is done. Okay. So I'll show you what is done. So first, now let's look at the parameterization. What you want to learn is, I'm at some time t, I want to learn how to go one time step back. Okay. So theta is the parameterization. This is a learned distribution for this vector of tokens. First, we are going to parameterize it as conditional product form, meaning each given this entire vector, there is, of course, ZT is a dependent vector. It's not independent. I mean, language has lots of dependencies. So ZT is some vector, condition on the whole vector. ZT is, what kind of vector is it right now? It is some elements are masked, some are actually tokens. That's the generic form of a ZT. Parameterize the previous time step as conditional product form given ZT. Okay, so note that this is not ZTL. That's what I mean by the whole vector. This is actually ZT itself. Okay. And I'm going to use this dot equal to denote a parameterization or a design choice. Okay, in this thing. And now and equal to essentially means it's a mathematical relation. Given all the definitions we have so far, we can use that.
Just the notation there. PFET actually knows it's not just the value of ZSL, it also has a position. Or no?
Sorry.
So the right of the product,
Mm-hmm.
you've got that thing. Is L actually also an argument?
Yes, yeah, that's why it's a notation. So this is actually, okay, if you want to do it properly, S, comma, T, comma, L.
Right.
Okay, then I could do dot given dot. Okay, this is what I mean. This is why I was careful about my earlier notation. We are encoding in the arguments a lot about the distribution itself in this notation.
Are learning a different network kind of at every time step, or you just?
We'll see. Right now I've capped, but we will see what we are learning at any point in time. Okay, but I'm just telling you what this is. In general, right now, this is the way it's set up. And then P theta is trained to approximate the reverse posterior. What do I mean by that? Okay. So we need some more notation. What we are going to, first let me describe in words, and then we'll describe in the equation itself. So let's just look at this. This box is going to return, if you're implemented, is the following. You're given a sequence of tokens. This is just a sequence of integers. And what you're going to predict is for the nth position at one time step in the past, a 50,000 dimensional vector. Okay, where each coordinate is the probability that what it thinks is going to be that particular word from the vocabulary. And the last element in that vector will be the probability that it's going to be a mask. Okay, if things were, for example, if ZT was such that in that position it was previously masked, it could continue to remain masked. So you could put some probability there too. Okay, so what you predict P theta is essentially a probability vector of 50,000 odd dimensions. Okay, now in words, before we go, let's think about the image thing. I have a noisy latent image. How did DDPM predict this? You took this and predicted the conditional expectation of x0 given zt. Going back to our earlier lecture, right? We were at some point time t. We had a zt, which is a latent vector. It is now just a vector in some RD dimensional space. Using that, you computed the score. But we saw that the score is affine in the conditional expectation. That's what we did using tweedy, which means that what you are doing is you are predicting what x0 was effectively. Once you predicted x0, you renoised it to some level using the forward process to get at time t minus 1. That the way you did, you could implement it in different ways, but this is effectively what is done. Here, we are not going to predict a conditional expectation. What we want to do is the following. Given zt, you're going to predict a categorical distribution of x0 and then decide whether you're going to remask it or not at time t s, which is t minus 1. So that's the pipeline that's going to happen for discrete diffusion. So let me repeat. You're at time t. There's a particular, you got some masked, some unmasked tokens. Look at that vector. Using that, predict a categorical distribution at 0, meaning for you predict, suppose let me just in particular just look at the health token. Okay. Why am I looking at only the health token? Because I've already decided things are product form here, the one step. So I'm just looking at this particular term. Okay, I've just picked a token, health token. But I've got the whole set of tokens, not just the health token. At time t, I've got the whole set of tokens, including the health, which may or may not be masked. I take that whole sequence and predict at x0 what the token value is. Okay. What do I mean by predict what the token value is? It's not a conditional expectation, it's a categorical distribution for that point. So now I've got a categorical distribution of that particular token at time 0. And then I'm going to decide next step whether to go from t to s, which is t minus 1. I will just decide whether I want to take this and keep it as is, whatever I predicted, meaning or do I remask?
Where in this pipeline are you using this?
Hang on.
You could one shot all of X and not assume that.
No, I'm just doing one. The learned function is this. This is what you're learning. If this is a completely different function you're going to learn. I'm just trying to learn this right now.
But you said if I have some ZT, then
I will try to predict x0L.
the distribution over all tokens.
No, of one token, not the joint distribution over all tokens. I'm predicting the marginal distribution over the health token at time 0. It's very, very different from the joint distribution of all tokens. Yes.
Oh.
Exactly. And then product form, and then renoise each one. I'm going to write it. That's why I told it in English. Now I need to build up some notation so that it's clear. Yes, Sujay.
So there are two things here. One is that you're going all the way from the teeth noise to fully T. And the other one is like, what is the Fourier modeling, right? So the first one of like going straight from T to full T noise, that's what happens in images also, right?
No, what
You
you,
have
but,
the image change.
it is, but it's a condition that mathematically is a conditional expect. So it's you're not in images. What you're predicting is the conditional expectation of x0 given xt. This is not a product marginal thing. It's a that's a separate story. That's not what I'm highlighting there. I'm highlighting that the score function is giving a conditional expectation. Why? What is 3D? So okay, let's think about what you're doing in continuous diffusion. You start at xt, a random variable. You take a small step according to the grad log pt of x. But what does that mean physically? Grad log pt of x is x plus. I'm just talking about inference.
No, but change,
Huh.
right, for images, right? You straight away predict x0 from xt.
Correct.
Right? Just like you did here.
The reason that is correct there is because of all this 3D business. That again, you're using the 3D the other way around, that the conditional expectation is affine in the score. So you want to learn this. You want to learn this score there. That's the goal. We know that the conditional expectation and the score are affinely related. That's the whole point of DDPM inference. Meaning, the score equal to x plus grad log p. Expected value of x0 given xt is equal to grad log pt of x plus x, so with some constant in that. So now I need to therefore learn conditional expectation of x0 given xt. And how do I do that? That's the training thing. I will take an image, I will noise it, and then regression will tell me how to predict this conditional expectation. The whole game there is to try to predict a conditional expectation. That's all I'm in a conceptual level. How you do it is what you said, the details. But this is the game there. Here, you're not trying to predict a conditional expectation. You're predicting a categorical distribution. That's what I'm trying to highlight. That is what I was trying to highlight. Okay. It's a different prediction. Huh? Well, it could be summation jpj or something like that. I could give a value for it. It's some mean of this vector. Yes. I can give you a definition, but it's not clear it's useful. But yes, yes, precisely. Precisely. There things were, that made sense there because the Gaussian world has a notion of distance. Here it's not clear if j and j, if width and is are near each other or not, even if they're integer-wise close. That's, yeah.
The distribution vector that you're predicting kind of like an expectation. I mean, I see.
Let me go through the discussion and we'll come back to this. I just, let me just I'll come back to your question in a few minutes, okay? So now, given this discussion, this is what you're trying to predict. Remember, we wanted to find p theta. We are going to push the parameterization to x theta. So x theta of zt is a vector on the simplex for each token, okay? This is a distribution, meaning it sums to, if you sum over all the coordinates of x theta, so this is the notation I'm using here, okay, which is, look at this. This is a vector. What is in red box is a vector. Look at the jth element of it, and sum over all j's. So all I'm saying is that x theta lies on is this vector lying on the simplex. So you're trying. So given zt, you're predicting a vector on this on the k simplex. Okay. And now this is the parameterization you're going to use. P theta is what is the reverse one step. You want to predict what we are at the lth token. Given the previous zt, you want to figure out what a distribution over that one time step in the past, what the vector should be. You're going to say that the parameterization is the following. We know the following clean expression. If I knew both zt and xl, meaning I want to figure out what this token is, I know everything. Oh, I guess on the video people don't see what I'm doing. Okay, so okay, I know at time s I want to figure out what this is. I know at time t I know what the state is, and at time 0 I know what the state is, and I want to figure out what this intermediate thing is. Then you just look at that particular, and I'm interested in just one particular token. Well, look at this token, look at this token. If they're the same, this must be the same. If these are different, then this must be a mask, and this is not a mask. So this is either a mask or not a mask, and we found the probabilities associated with it. Okay, that's basically what this was. So the way you're going to parameterize p theta is the following now. P theta is going to do the following. First, look at this inference posterior, assuming that the lth coordinate is some j, the jth integer. Then I have a categorical probability for this. And now, what's the probability of this being j? It is what your learned function is predicting. It is predicting that given zt at the lth position at time 0, it is just j. That's the probability. Because what you're predicting is not an expectation, it's this categorical distribution. So putting these two together, then, so effectively the interpretation is what you're learning to approximate is this. Okay, it's not q of zs given zt. It is q of zsl given zt comma xl is what the reverse posterior is trying to. Yes. Summation over j. So where? This is the jth element of this. Okay, that's this is a vector. I'm just looking at the jth element of that vector. It's not a summation. Okay, so the way it's written is not this though, which is why I'll show you how the notation is written. Again, that is somewhat delicate. So you should learn how to interpret this statement in a second. But before I get to that, let's finish this discussion. Remember what Q was. Q was basically, if my future step was unmasked, I remain the same. If the future step was masked, then right now I know what I started with. With some probability, I'm the token. With some other probability, I'm the mask. We derived what these things were. Okay, we know this expression.
About
This notation. Let's not worry about the notation. I will give you the notation the way it's written in the community. I think that's because this is the only time you're going to see this notation. Okay, if this is the mathematically correct, but if you don't like it, I'm never going to use that notation again.
What's the better way of?
I'm going to show it to you in a second.
Okay.
Okay, it's in a page. We are getting to that. Okay. So this is the better way to say that same thing. The probability, the learned probability given of ZT, given given ZT, you want to predict ZSL. This is just a vector in 50,000 dimensions on the simplex. It is either equal to mask with this probability or equal to this vector, which has 0 position at mask. So if you look at the vector, the categorical distribution dimension, there are all the words in the dictionary and then one extra point. If you predict what it is going, you know that you don't start with language having mask. It's a fake thing. So the x theta you're going to predict will be a categorical distribution, will be a distribution with 0 in the last position and everything else adding up to 1. Right? That's the structure of that distribution. So that's what this x theta is. This is your prediction. You say that you stick to your prediction with some probability, or with some other probability, you continue to remain masked. So at time t, suppose the else coordinate was masked, you will continue to be masked at one time step in the past with this probability. And it could be any other word according to those with, so in particular, what's the probability this is equal to the word j? It is this times the jth coordinate of this. Does it make sense? And the way this is written is this. So this is the other overload of the notation, which can get confusing. So normally when you write a conditional probability, you think of this as a token, this as a token, this as a token. That's not true. This is written differently. This is written as this is a token, this is a token, this is a vector, a distribution. This is a mixture of tokens. So you're overloading this definition to allow mixture of tokens to be in its argument. Okay. The reason it works is because for the mass model, it's very clean. It just basically becomes this mixture of tokens there. So in terms of form, look at these two expressions now. Look at the expression for how Q looked like. This was a token, okay? And if it's this token, then that token appeared there. Now, when you're not dealing with tokens, look at the way the expression P has. It has that distribution there. So you can just overload this notation of the Q to put in this thing and still everything works, okay? Only the way you derive it is somewhat more careful, but it looks like it is as though the Q could take not just a one hot, but anything else in and give you a distribution. Now, does that answer your question or how it's written? I think this is what you are trying to get to at some point. Or is there?
I'm still wondering why do we have to do this independently for all of the?
Of course, because you're not trying, because learning a joint distribution is much more complex. Let's say there are two tokens. Okay, I want to predict joint distribution of given ZT. Suppose I want to predict the joint distribution of those two tokens. That parameterization is much, much harder than trying to learn the margin of the first one, learn the margin of the second one. Okay, it's a much simpler problem. The sample complexity of learning that is much harder.
Text really was in it,
but good. So that's really the thing. That's why you don't try to denoise in one step. That's the same iterative denoising. Because ZT, no, one step at a time. I will locally assume their product form with this thing, but then don't trust that, renoise it. I'll get to one time step next, then locally assume then it is, because now ZS after this thing has some joint distribution. Okay.
Let's see the details to that, yeah, because it seems basically I think what Jacob's saying is that if I denoise 2 according to an IID thing, there's like no chance.
Yes, but it's not. It's conditional. But the point is, it's conditional. It's condition. They're all on the same conditioning. That's really what's coupling them. It's not that the marginal that the distribution of x0 by doing this is not. Okay, what they join. Let's write this. I think this will.
Let's finish the procedure because we haven't seen the renoise.
Done. You have seen the renoising part. You've seen the whole thing. It is just renoising means mask. Because what is Q? the reverse posterior said that I give you, I look at suppose that at some time t, the Lth token is a mask. Then at time t minus 1, which is S, it continues to remain a mask, or it is the original token. Now, I'm going to use this as a surrogate for the P. I'll just use this formula, but instead of XL, I'll put my predictor, which means I'll get X theta L here, which means this is sort of the renoising. It's saying I will use my prediction with this probability or continue to remain a mask with this probability.
Yeah, but as you
That's the parameterization. We have done the whole thing in one shot now.
put in
This is a model. Sujay wants to say something. Yeah.
Yeah. I give an advertisement for like
Yeah.
tomorrow's talk. But what Sanjay is saying is absolutely right. Like the way it's trained, the only way to do exact inference is one at a time. The moment you do even more than one at a time, you're doing it wrong.
You're doing the wrong thing. You can fix it. There are, I mean, recent to deal with all this, there are papers, including Sujay's, but as I said, this is not a research talk. I'm describing the base model so that you understand the notation and the language. The purpose of this class is not to get you to today's this.
So I guess you haven't said that, like, if I had this categorical ZS given ZT, and then what do I do with it? You're saying I could unmask one at a time.
I'm just giving you the distribution of, I have now given you the margin. That's your problem. That's how you sample. No, you can sample one at a time and it's done. You'll get a model, you'll get an answer. I don't give you any guarantee. I've not said that, look.
If I say two at a time, it's not, you're not telling me it's going to be the right thing.
Of course, I never said anything is the right thing. Okay, I'm telling you this model. I'm going to tell you how it's trained, what the setting, and what the lower bound is. I'm not telling you anything about whether this is correct or wrong or any such thing in terms of how close it is to the. It's like I'm giving you an algorithm and the notation. That's all I'm doing right now.
Phrases are not assuming that text is really independent, but just saying I'm just going to learn the margins. That's it.
It's not. It's because it's a condition. It's if you just did that, then yeah, of course this will be completely nonsense. If I just learning the whole, I'm not saying that I'm not saying that input is product form. X is product form. I'm saying X given ZT is product form for one step. That is my local approximation. So the joint distribution of that will also integrate over the joint of if ZT was somehow really nice initial condition, okay, which had encoded all the right dependencies and had enough structure. For example, maybe ZT was sort of anchors or something, okay? Then you're in good shape because once you know a few things, everything else could be product form. There are different ways to deal with it. As I said, Sujay is going to talk about another way to deal with it in tomorrow's talk, but and anchoring deals with this in some other way and so on.
And it's forced on, as far as I understand, by the transformer architecture. Right? So in the transformer architecture, you have like n parallel outcomes, right? And each one is individually conditioned on the input, right? But there is no way that
you could in the following way. Hang on.
Bidirectional.
It will not give. No.
Right, but finally in the end, you have an individual logic which depends only on
your function is not a. So if you want to learn, let's say there are really, if you want to learn the joint, the way you do it is the following for two tokens. You'd generalize the state space to all doublets and predict a joint because you need to predict a joint distribution, not a product of marginal distributions. Okay, your state space will be exponentially larger. It will be L-fold larger. In a transformer, you're not going to deal with vocabularies, but you'll try to generate the input sentence. It will be a distribution over sentences as opposed to words. That is really what joint distributions are. No. Even with, I could come up with a completely different model, okay? Let's say there are two words. Any sentence is a sequence of two words, and each word can be one of, say, 4 things. Then, so it's 1, 2, 3, 4, 1, 2, 3, 4 for each one. What this is predicting is, given ZT, which one of 1, 2, 3, 4 it is. Given ZT for the second one, what of 1, 2, 3, 4 it is. The other way of doing it. Look at 1, 1, 1, 2, 1, 3, 1, 4, up to 4, 4. There are 16 meta words. Yeah. And then given ZT, I could predict a distribution of those 16 meta words. That is the joint. That is really what the sample complexity of joint learning is.
Discretization goes to, as you have infinite discretization steps, you will automatically only have.
Good. This is the other thing. This is now you're asking whether as in the limit as these number of steps become small, is this actually the correct posterior? And that is that's not obvious, but yes. If you take tiny steps of product form, what you're saying is higher order dependencies in small time steps don't matter. It's a second order term and not a first order term. If you believe that is true because of some smoothness, then this is correct in some limiting sense. And that is exactly what we'll show using the discrete flow matching next time. It's the elbow versus DFM. Okay, this is going to be justified using an elbow loss. You can now go to flow matching and say in the continuous flow, this is effectively what, even in the DD, okay, that's in the analogy of this kind of thing, not quite correct, but roughly the analogy of this in the diffusion, continuous diffusion world with images was the following. I am predicting a conditional expectation, which is a blurry image, and taking that as the base. Really what I should do is be on the manifold of images. I'm not, but things seems to work anyway. Okay, the reason is in the discrete, if you take small enough steps, it shouldn't matter. Okay, it's an imperfect analogy, but that's roughly the equivalent analogy here, this parameterization.
But if you had like E, for example, like much larger,
yes,
then it won't matter.
Exactly. And that's what we will see from the flow matching. It's all correct in the continuous limit. But then it will also go back to Sujay's point, which means you're essentially there. By definition, you're just decoding one token at a time in the continuous limit. And then you take the limit really small. In fact, in the continuous limit, at every time step, you will decode nothing most of the time. Yeah. Very, very rarely you'll decode one thing, that jump. And in that limit, everything is correct. Because you're never doing the joint. You're never using the product form. Yeah. Okay? Essentially. Okay? That's right. So this is an architecture which is true, which is correct in the limit. And the same analogy actually holds in continuous diffusion too. There we are doing conditional expectations and assuming that the manifold could be super curved and the conditional expectation could be completely off the image manifold. Even then we were using that and things worked. Because in the small time step, again, the same kind of thing happens in a different sense. Okay. All right. So now you understand the parameterization of this thing. And so the way this is written is this. That is, the parameterization is such that you use this predicted probability vector and use that in the true reverse posterior. And this has two properties. In the literature, it's called zero masking and carryover unmasking. Zero masking means that whatever you predict will not predict a mask. We said that's true, but look at the notation. Because X is a category, now we'll start doing all the calculations with inner products because this thing. So a mask is nothing but one hot with the last element being one. X theta, all this saying is X theta has support over all but the last coordinate, this vector, and this inner product is 0. And the other statement is carryover unmasking. In terms of algebra, it basically says the following. If something was unmasked, at the previous time step, it will continue to remain unmasked. Okay? And the way you write this is the following. It's unmasked means this thing is actually a vector which is all zeros, one somewhere, and rest is zeros. That's what this vector is. So this is a distribution, again, over the same support. If this means that the inner product is 1, that means this also should align the 1 where it was previously. That's all it means. So this is all notation, but when you see these kinds of things thrown around, oh, we'll use this property or that property, it could look confusing till you realize that that's all has happened. Okay. I have 10 minutes left. I'll start talking about how to derive the training loss, finish it next time, and then move to flow models. Okay. How do you train this model? So recall the elbow or the negative elbow in literature. What we did is the following, right? We started with okay. Maybe before that. I made the statement that Z and X0 may be different. In practice, sometimes it's different because, hey, you come up with a bunch of tokens, but maybe for some application, not necessarily language, but something else, you want to permute these tokens in some way. Or you may want to extract a few tokens from this, which is all you care about for some other application. Say, maybe I just need to answer something, okay? Or I want some links in some protein model or something like that. You could potentially think of Z0 and X being different. So this formulation allows the first step of X for quote unquote post-processing, and then you start from Z0. This is a small nuance. So, but in what I'm writing, I think I'll sometimes have X and Z0 separate, sometimes the same. Okay. What is the training loss? And we'll start deriving it. This is the training loss. So this first step is about X and Z, some cross entropy on X and Z0. We'll ignore for right now, it's just 0. The key thing is the following. It's basically a weighted cross entropy loss between, at each time remember that in all this stuff, all the learning has been pushed to only one thing, which is predicting X0. Okay, you're predicting the true, you're predicting a categorical distribution over the initial token, right? After that, everything else is just, I'm using known functions, Q of ZS given ZT comma X, and all are known functions. The only thing that's being learned is, if I'm at ZT, how do I predict Z X L? That's the only thing, and that's a categorical distribution you're trying to predict. So here, so you have a cross entropy loss on that. It's weighted appropriately according to the generative process, and that's all there is to it. So this is a sort of simple answer, but we can talk about why exactly this is, where exactly is this coming from, and this will come from the elbow. Okay, so the claim essentially is, if the negative log likelihood is bounded by this, and also coming back to the two discussions we had, both which we had with what Sundar said and what Sujay said. In some limiting sense, hopefully this is inequal and this is close. Okay. If you go to a flow model, in some sense, where you almost you decode very rarely, and whenever you decode with a high probability, you decode only one, then you should be you should be able to prove something more. Just like continuous. The SDE view of the world versus the elbow view of the world. Yes.
Discrete flow match, it's continuous time.
Yes.
That means it's one.
Yes.
Cannot go.
Yes.
Like it cannot model.
It's non-explosive. It's a non-explosive Poisson process.
Cannot model more than one.
You can.
Simultaneous and one.
You can, but the state space will blow up. This is what I sort of alluded to. You basically, even here you could have done this. I don't want to, I will look at pairs of words as a new word and then work on that state space. So in the discrete flow matching, they start with arbitrary things, but then they say the unmasking is coordinate-wise vertical or horizontal jumps. You can't jump any other way, which effectively means one at a time. Okay. Yes, which is why whichever way you do it, finally the system you build is essentially exactly the same, whether you're using the flow matching world or this. It's just giving a different way to reason about this. That's all. Okay. The claim is that this loss function we looked at is an upper bound on the negative log likelihood, just like what we did when we did the DDPM discussion. And to do that, I have about 6 or 7 minutes. Let me start this just so that we refresh about what the elbow is. And then next class, we'll actually derive this. Okay. Recall what the elbow was. We had a log likelihood. We enlarged it to some latent space. We were allowed to go to a latent space. And then in that latent space, you could basically have an encoder and decoder, and you use Jensen's to get a particular lower bound loss. Again, I don't want to repeat all this. If you want to remember this, go back to lecture 8 and 10. We have spent a whole lecture on each one of these kinds of things. Okay, so the important, and then we went to multi-stage latent in lecture number 10. And we said that, well, the way you would sort of get bound the log likelihood to the elbow is look at essentially the term which you need to optimize is log ratios of probabilities. One is the true generative model. The other is the one-step reverse process. And you're trying to do the KL on that, essentially. It's a KL loss minimizer. Okay. This is one-step reverse. This is the true reverse. All this is from past lectures. Now, in this case, what we are going to show is that you just you substitute exactly the same setting in. You're going to get essentially here you'll get the true reverse posterior. What we are here trying to approximate is p theta is trying to approximate the reverse posterior, meaning ZS given ZT and X. Actually ZSL, but there'll be one more product form. We have just written one of these terms. So all this product stuff will happen. The log will become a sum and all that business. Okay, but essentially this is what you're trying to approximate. So the elbow, just plug in the elbow into the setting, will give a KL between what you're trying to learn and what the ground truth of that is. And now we need to simplify this whole thing for the case of the mass model and show that for the mass model, this term will come down to be something very simple, which is just simply look at what you're trying to predict, what the actual thing is. What the actual token during training is 1 hot, right? You know what the token value is. That means XL is 1 at some particular location, 0 everywhere else. That's your training data set. What you're trying to predict is a distribution that tries to collapse into that point as much as possible. That's all. That's your X theta. And then you train with this loss. Next time, actually, I'll derive this and we'll continue from here. Thanks.